So our first definition, kind of a weird one, a term called undefined terms. Now we were just talking about vocabulary, but within part of that vocabulary, we're going to have things that we do not really have a formal definition for. And these are called undefined terms. They're things that are only explained using examples and descriptions. Things that are only explained using examples and descriptions. So that right there could easily be a term that you're going to need to know for the test. So on the test, I would give you things only explained using examples and descriptions. You would need to be able to put on the blank. That's undefined terms. Most of the things that we're going to talk about today, the really, really basic stuff in geometry, they're all going to be considered to be undefined terms. I'll be able to give you examples. I'll be able to describe it for you. It's not something I can give a definition for, and we'll kind of talk about why as we go through stuff. And the first one, as basic as it can get, is a point. Not a new concept at all. You all have thought about points a lot. We've done them in here already. When we plotted ordered pairs on the coordinate plane. First descriptor, again, not a definition, just a description. A point has no size. Okay? When we put it on a paper, if it's just a single dot, but even that dot is just representing something. Somebody able to say, what does a point represent? What's the point of a point? Think about how you used them on the coordinate plane. What did a point tell you about? Yeah, notice how you're saying the word there, where. That's the question that a point answers. Where are you? Where is that ordered pair? Where is something located? That's the purpose of a point, to let you know where something is at. As far as naming them, you've done this already. It's not going to change from what you did in algebra and what we did in chapter 0. Points are named using capital letters. Points are named using capital letters. You're going to see this in two ways. Let's say I want to draw a point. I just put my dot. And then usually, typically, right next to that, you're going to see the capital letter that we'll use in name. Okay? So that's how you're going to see it actually represented on a plane. And then if you want to talk about this, when you name it, you just use that capital letter. There's no symbol for point. You don't have to write the word point in this course and really anything. If you see just a capital letter like that in this kind of context, you can be sure that it's talking about a point. So I would read that instead of just P, I would say point P. So read it like that when you see it, but you do not have to write the word point, and there's no symbol when you're writing it out. Next, lines. You kind of notice as we go through this, we start with points, as simple as we can get. Combine points and you get a line. And then we'll look at what happens when you combine lines, what you can get, and keep building up from there. What can you tell me that you already know about lines? Anything you can use to describe them? Start shouting stuff out. Okay. Okay, so he's saying, if I've got 2 points, is that enough to make a line? Yeah, that's the minimum. As long as you've got 2 points, you can always connect those with a line. And that's actually something we'll define later on, so that's a good property. What else do we know about them? What? Okay, so if we combine lines, we are going to get something else. We'll see that later on. How about drawing the lines on the coordinate plane? What do you make sure you do? They got to be straight. And what else do you always put on? What always goes on the ends? The arrows. And why do the arrows go there? It shows it never ends. So that's some pretty good stuff. So far you guys say 2 points are enough to make a line. If I combine lines, I get other stuff. And we put arrows on there to show they go on forever, and they've got to be straight. So my first point does not contradict what you said earlier, because you do only need 2 points, but once you make that line, you've created an infinite number of points. So a line is made up of an infinite number of points. Infinity, that's a concept that for most of us, it's not really that easy to think about because our brains like things that are very concrete and finite. And this is what it is, and this is what we can work with. But in geometry, this is a course where you're really going to start thinking about infinity, especially in terms of lines and things like that. Think about, and I want you to draw this with me, if I draw a line. And let's say this line is going to represent the real number line. So let's say here I've got 0, and here I've got 1. I'm going to put a point on each of those. Okay? So I start with 2 points, like Colin said earlier. That was enough. And I made a line going between them or something that almost looks like a line. Then how many points are between those 2 points? Can I make a point in the middle? Yeah, if it's right in the middle, where's that going to be at? A half. Could I make a point between 0 and a half? Where would it be at? A quarter. Could I keep going? Is there ever going to be a point where I can't keep going? Physically, I mean, I'm going to run out of space and I can't draw, but mathematically, I would go down to an 8, 16, 32, 64, forever and forever and forever getting smaller, and I'm never going to be done. And that's that concept of infinity. I cannot stop. So between any 2 points, there's always an infinite number of other points because you can always deal with fractions. That kind of helps. That make a little bit more sense? Cool. The point that you all already know, like I told me earlier, lines always have arrows on both ends to show that they extend forever in both directions. So arrows on both ends show they extend forever in both directions. It's very important. I know it seems simple, but it's very important that you understand that's what makes a line a line. Because as we go through chapter 1, we're going to have some things that don't have arrows on either ends, and then we'll have some things that only have an arrow on one end. And you're going to need to be able to tell what you got when and what to call it. So for a line, forever in both directions. And then we're also going to care about naming the lines. That's something you'll do a lot of in today's homework. You've got 2 options, and it just kind of depends on what you're given to begin with. You're either going to use a lowercase letter, or you're going to choose 2 points on the line. I'll draw another line. So I got my arrows on both ends. And then label it just like I'm labeled it. Point A, we'll put there. Put point B here in the middle between them. And then point C there. And then next to it, I'm just going to put a lowercase l. And usually you're going to see those lower cases as cursive letters. And that means I've got a bunch of choices about how I name this line. So first thing it says, I can name it using the lowercase letter. So there you only really have one choice. So I would call this, and actually write out the word line, and then use the lowercase l. That's one name that I could use to identify. So if I say line L, you'd be able to look at this figure and be like, oh, that's the one he's talking about. What's the other way it says I can name it? So do I have a choice there? Because how many points did I give you? 3. So I can choose any 2 of those in any order and name it that way. So what 2 do you want to use first? Okay, so I could go AB, and then my symbol for a line is, imagine this, a line. So I put capital A, capital B, and then over the top of those, I draw a line. So because it's a line, what did I make sure to put on the ends? What other name could I give this? AC could work. So capital A, capital C. Anything else? BC could work. Could I have even more names if I wanted to? Yeah, or yeah. The order doesn't matter either. So any of those 6 that we just either said or have written up here, fine. And typically you're only going to need one name. So go with it on a line, any 2 points, any order, that's it. Or you can use the lowercase if it's there. We've got 2 other terms next that relate back to what a line is, and they are collinear, points that lie on the same line. We just saw an example of 3 collinear points. Basically, to check to see if they're collinear, imagine or try, can you draw a straight line that goes through all those points? If your answer is yes, they're collinear. If the answer is no, even if it's just 1 point that's off, you got to say no. One thing I do want to look at, we'll do this a lot in here, if we can break down these words and their roots, it's going to help us remember what they are a lot more. This prefix co, what does that usually mean if you put co in front of a word? Part of, or the. What are some other words that start with co? What? Continue. I don't know if that would apply. What? Copay. Usually means like same. Like if you're cooperating, you're doing the same kind of work. Copay means you're paying towards the same thing. So co, when you see that out in front in this class, it's almost always going to mean same. And then look at linear. What do you already know that pretty much is? Yeah. So that tells you what the definition is right there. Collinear literally means same line. Points that are on the same line. So our next one is non-collinear. What's that going to mean? Exactly. Non-collinear, points that do not lie on the same line. So an example of what those could look like, I'm going to plot 3 points. Point A, point B, point C. As a whole, are A, B, and C collinear or non-collinear? Not, because there is no way that I can draw a single line that goes through all 3. But what if I just asked, are A and B collinear? What about B and C? A and C? If I gave you any 2 points, would you ever be able to say no to that? This kind of comes back to what Colin said at the very beginning. If I've got 2 points, I can always connect 2 points with 1. So 2 points must be collinear. But once you move up to 3, maybe yes or no, and you got to look at it. So that'll be a question to answer, and we'll use those words a lot in this class, so know them very well. The last geometric figure that we're going to talk about today is the plane. When I say plane, am I talking about the thing you fly in? No. This one's spelled the same. I'm also not talking about grassy fields, because it's not spelled the right way. And I'm also not talking about boring things, because it's not spelled that way either. When I'm talking about the geometric plane, what am I talking about? Geometry stuff, yeah. Can we describe it at all, though? You've used one of them a whole lot already. What's the one plane you're really familiar with? The coordinate plane. So how could you maybe describe what that is? The grid on a what? How would you define a paper? It is flat. That's really the key to being a plane. It's something that's flat. And with the coordinate plane, you take something that's flat, you slap that grid on top of it, and that's what makes it a coordinate plane. So for our definition, we're going to say a plane can be any flat surface. A plane can be any flat surface. It's like a piece of paper I was holding up. A great example of what a plane can be. So look around the room. What are some other things that could count as planes? Your desktop, the tablet, the blackboard, the smartboard, floor, the ceiling, the walls. All that, they're flat surfaces. They could count as planes. Just like lines, where there was a minimum of 2 points to make it, planes have a minimum number as well, and they are 3 non-collinear points. This one's a little bit harder to visualize, but try to imagine that out here in space, so kind of look up here, out here in space, I got 3 points just kind of floating. So 3 points wherever I want them, but just there's 3 of them floating here. What this is saying is, if I want to connect those or I want to cut through them with a flat surface, only one of them will do. Just like with 2 points, there's only one line that'll go between them. With 3 points, there's only one plane that'll go between them. And we're kind of getting a little 3D with that, which makes it a little harder to visualize or represent this way. So that's the idea. You have 3 points floating somewhere. Only one flat surface will go between them. The key is, though, they have to be what kind of points? So they can't be, what does it mean to be noncollinear? Not on the same line. If they're collinear, an infinite number of planes would be able to go through them. Naming a plane. This is done by a capital letter or 3 non-collinear points on that. So I want you to sketch what I just sketched there. My line tool is not working right now, so forgive the shoddy shapes that are up there. And typically in your book or in my notes, that's how we're going to represent a plane. And that kind of shows that it's not just going to stop at those edges, it's going to keep going. Kind of like the coordinate plane where on the axes you've got arrows on the ends that show that it keeps going in all directions. Same thing with this. So in one corner, let's put a capital R. And let's put some points here. Put point A, point B, point C, and over here, point D. I'm going to give a couple different names to this. The first point, I can name it using a capital letter. And this is where it's a little tricky, but not that bad. What else gets named with a single capital letter? A. From earlier today? First thing we did? A point. Which letter up there is not connected to a point? So that's what I could call it. I could call this plane R. So just look for the capital letter that's not touching a point. Typically, it'll be in one of the corners. The other way I could name it is with 3 non-collinear points. So I could call it plane. What's one set of points that I could use that are non-collinear? BCD could work, so jot that one down. BCD. Are there others combinations that I could use? A what? Could ABC work? That's actually the one that won't. Why not? Yeah, look at ABC. I can connect those, pretend like I did, connect those with a line. So those are collinear, so they don't count. But I could use ABD, BCD, DCA, as long as they're non-collinear. Last thing that we're really spending much time on are intersections. You already know about these to some extent. How would you describe to me what an intersection is? Okay, what happens at that four-way? That's a good way to start it. What are the roads doing?
Crossing.
They're what?
Crossing.
They're crossing. Yeah, you don't want to say intersection because that's what we're trying to find. Yeah, they're crossing. What geometric figure might you define a road as? What would it be closest to? Like just the road itself? Think about the things we talked about today. Would it be more like a point, a line, or a plane? Yeah, I would say line. So think about whenever you got that four-way and you got those two lines intersecting, what would you describe that intersection as? A point, line, or a plane? A point. You kind of think about it if you're looking at a map. You got your two roads crossing, and they cross at a single point. That's how lines cross. They cross at points. The way that we'll define intersection is going to be kind of broad. This way, it applies to every geometric figure, not just lines, not just planes, but anything we want. The intersection of two or more geometric figures is the set of points they have in common. The set of points they have in common. Let's look at how this works in each case. We already talked about when two lines intersect, they intersect at a single point. So if you're asked, okay, where do these two lines intersect, you're going to have a single point, and that's it. We kind of already looked at that before when we were solving the systems of equations. They either touched once, they didn't touch at all, or they were right on top of each other. There wasn't really any other option because that's how lines work. Planes are going to get a little weirder. And for this, let's just kind of look at the walls of the roof. So everybody look at that corner up there. The one in that corner. This front wall is a plane. That back wall there is a plane. So they're crossing in that corner. How would you describe what that corner is? It's a what? It's a line. So that's how planes intersect. When you got two planes that meet up, you can kind of also think about it like if you take two pieces of paper and I put these next to each other, they're touching all along this area here, which would be a line. So let's just write that. Planes intersect at a line. When you kind of think about it, it's the thing that's lower than. Like you start with lines, their intersection is a point. The next step down. You start with a plane, their intersection is going to be a line. The next thing down. And then last term for today. Sorry, second to last term. We got a definition for definition. Which I know seems weird, but in geometry especially, we want to make sure that we're building up things. So at this point, you know what you know from the day. So you're allowed to use all that, but I don't really want you pulling from things that we haven't discussed yet and haven't proven to be true yet. All of our definitions are going to be explained using our undefined terms from today, the point, line, and plane, and or other defined terms. So things that we've already given definitions for. And that's one thing that separates mathematics from other courses by quite a bit. We want to be really, really cautious that everything that we do is right. Because think about, unlike other fields, how often in mathematics have we ever said, oh wait, that was completely wrong and we need to fix all that? Can you guess how often that happens? Never. Because everything has to be proven before we actually go forward with it. And then we don't use things to prove other things unless those things have been proven. And when we prove something, we have shown that it is absolutely true. Because we're going to work on that kind of stuff a lot in this course. So I will continue to answer that question as we go through the semester. It's a lot of using rules of logic and things like that. And where it's a little bit stronger, unlike, let's say, science, you're going to do an experiment over and over and over again to show that something works that way. But what happens when that experiment doesn't work the way it should one time? Something's got to change. That throws everything off because it only has to be wrong once to be untrue. Whereas in math, we don't prove things using experiments. We prove things using logic, and that makes it so it is absolutely true. Examples don't prove truth in mathematics. They can lend itself to kind of guiding you to that truth, but they don't really show that. And that's something we'll work on a lot in chapter 2. Typically, here's how it works in math. Like, we don't necessarily start with, okay, like, this is what I want to prove. We started with, okay, here's a question that I cannot answer. But I know that I should be able to answer it. So, and we'll kind of talk about some specific examples, but one that we do in calculus has to do with electricity. They knew that there had to be a way to do something. But the math that we had wouldn't let that happen. But physically, we know it works. So then they did some stuff with the math and figured out what would work there, and then proved some things along the way. But again, I'll keep answering that as we go on. Chapter 2, when we look at that, is all about proving things. So we'll get pretty in-depth in that. Now the last definition. Space. Kind of talking about space, as in like stars and emptiness. In a geometric sense, defined as a boundless. What would boundless mean? Without bound, or what's another way to say it, maybe? Infinite. You like that word because we're going to use a lot. So it does not end. No ends, no boundaries. Keeps going. 3D set of all points. So space literally means everything. Okay? Just like in the sense of space. And there's our first section of geometry. Your assignment. You've got a lot of time to work on. Page 8, you got problems 1 through 12 all, 14 through 38 evens, and 44 through 48 evens as well.